Good afternoon, everyone. Thank you so much to the Symposium Program Committee for inviting me and Sai to speak to you all about our program's post-exascale strategy. Let's see. All right, so the outline of our talk is I'll speak very briefly about what my program does, and then what the DOE Exascale Computing Initiative has been about for the last few years. And then Sai will talk about our program's post-exascale platform and R&D plans. And of course, software sustainability after the exascale computing project ends is a very key and active discussion topic for us right now. And then some final thoughts. So briefly, in case some of you may or may not know, there are actually two high-performance computing programs in the Department of Energy. So this program, the Advanced Scientific Computing Research, is in the Office of Science program, and actually in the audience, Sharon and Hal Finkel are our two DOE colleagues from headquarters, and they represent our sister HPC program under the Office of Science and Innovation. Sai and I, we sit over this column, and we support the Office of Defense Programs. So just to keep in mind that we have different responsibility and mission scope. But we work very well together. For decades, we discuss where we have overlapping interests and collaboration opportunities. Very briefly, I won't go through this, but the ASC program, we provide the predictive tools, science-based predictive tools for the U.S. Stockpile Stewardship Program. We build models, codes, validated codes, computing techniques, and then we also have to manage a balanced operational infrastructure, just so that we can guarantee what we do in the R&D projects will actually get to fruition for deployment to support our users to run the codes. This is the overall work breakdown structure of my program. Spanning from the codes, we build the models, we do verification, validation. This subprogram, Advanced Technology Development and Mitigation, some of you know it as ATDM. This is our exascale computing program. Sai manages the computational systems and software environment. And then we also operate, build, and upgrade our HPC centers at the 3 NNSA labs. And because of the scope of our program, I very much agree with Satoshi's comments this morning, how we need to have an integrated digital platform to enable our science. And this is our version of that position. The Exascale Computing Initiative, it includes NNSA and Office of Science as the two co-funding program offices. We do the acceleration of R&D, the Path Forward program. And then we deliver the computing capability, the computing platforms at the DOE labs. And just to show you that for us, for the exascale computing program, we procured the El Capitan system that will come to Livermore next year. We build and validate next generation models and codes. And of course, we have to also have a functioning software stack for LCAP and beyond, and also facility construction. you all have heard about the exascale computing project, so I won't belabor the details, but just know that there are 71 plus software products having been funded by ECP. So the really active question right now is what's going to happen to those products? What's going to happen to those project teams after ECP ends? Yeah, Satoshi's nodding, I'm nodding. And frankly, the answer right now for the federal program managers, we think we know how to do this, our plan, but it's going to require budget. It's going to require a lot of tight coordination between our program and Sharon's office. And Sai will sort of say a few words about our plans, but we really don't have a good concrete, line of sight on that topic yet. Just to show you the level of investment of the Exascale Path Forward program. DOE put in almost $260 million with the 6 vendors listed here also provided 40% cost share. And some of you have asked me and others at DOE, what will it take for us to do the next exascale computing R&D program? And this is, the question for this symposium, right? What do we do for the next generation system, platforms, et cetera? It will require a similar path forward for the next gen system development, right? And it requires that much funding from the US government. And that's the message I've been saying to my upper management. I'm not sure if they heard me, but I will keep repeating. So now I'm going to pass the mic over to Sai to talk about our post-exascale initiative programs, et cetera.
Thank you for the invite. It is wonderful to be here, especially in my new job. Many of you knew me before at Sandia. Now I have many more headaches than I had there to worry about. So for those of you who don't know how we procure machines at the NNSA, this is NNSA specific, we have 3 tracks. We have this advanced technology track. That's where our exascale, our largest scale-out platforms, that's kind of like our Fugaku technology track. We have this commodity track. I'll come back to some of these in a second. The commodity track, which is more like the kind of conventional, just standard nodes that you'd buy, the CPU nodes, lots of them. And then in the bottom down here, we have this advanced prototype systems track. And I think on Satoshi's slide this morning, there was a reference there to large-scale prototypes. And that's what that track is. So this is 1,000, 2,000 node scale prototypes of completely novel technologies that we're trying to test out for our program to de-risk the stuff above. So up in this track here, you can see El Capitan that Thuc just said was our exascale system, just about to turn up at the lab. So everybody cross your fingers and hope it's all going to go well. And then we're already right now planning for our post-exascale machines in the 26-27 timeframe. So we'll talk about some of the ideas that we have for that. Okay, go to the next slide. So what did, I feel like I'm going to repeat lots of Satoshi's observations, but with slightly different numbers in the next few slides. So what did we learn when we went from our pre-exascale systems to exascale systems? So this is going from on our Office of Science side, because we don't have an exascale system in the NNSA yet, but I think most of these ratios will still hold out. So you had this enormous compute increase, nearly 9 times increase. We had a memory bandwidth improvement of more like 5 on a good day. Network actually went up significantly, but it went up significantly because we purchased and spent a lot more money on network hardware. It did not go up because the hardware got substantially better. And the latency has stayed roughly the same. We've had improvements in latency, but we've had slowdowns through chiplets. And so when we sit down and we're going through surveying our codes right now at the NNSA for what our next set of requirements will be, I would agree with Satoshi that memory bandwidth, highlighted here in red, is where we've historically had really the most significant number of our performance issues. Compute is largely free, And believe it or not, we don't do that much compute. We spend most of the time generating addresses to go load things in from memory. So memory bandwidth is the focus of our next kind of suite of machines. And so what I was trying to draw for you here was, this is kind of size notional version of a future HPC machine that we think about. So in the middle here is this kind of Fugaku or LCAP or Frontier-like big HPC system. I think I will go on record as saying I still think this will be largely CPU or GPU or APU, where you squish the two together in the same socket. We'll still put down a very large number of those nodes. But what we're exploring right now, and I would agree with Satoshi as well, that a small part of our workload would be machine learning on the side. And so I just happened to put my favorite Cerebrus machine here on the side. You shouldn't read that this is the only technology we're going to use, but we do have these in-house, and we've been very impressed with the performance of them for some of our problems. And then sort of far over on the left is the thing that we're worrying about the most now. So if you're at a large HPC site, like some of our national labs, we're really good at compute. I think we've done that for a long period of time. What we do most of the time, though, is throw a large portion of our data away, and we're not really able to do the really good science that you've seen this morning from people who've got access to large data sets and machine learning. We throw it away because we just don't have enough storage, and it's incredibly hard to keep that data around when you have to do this at any appreciable speed. So we don't have enough performance in our data infrastructure, and we don't have enough size. And then just down here, we've got some sort of novel, maybe partitions, some CPU-only partitions, and some accelerator partitions. So if I was going to put this machine down today, I'd spend all my time worrying about the thing in the middle. I'd add some stuff around the side, and over time, I would sort of add some extra things around the side, and then I would be upgrading this big thing in the middle, right? Now, this brings some significant challenges taking this machine. Lots of PowerPoint architects just wave their hand and produce these machines, but actually producing them is going to require a lot of R&D. And so these are technology R&D programs that we have at NNSA, which are a start down this road. So Thuc just described path forward, which was hundreds of millions of dollars. The combined of these three things is kind of another $100 million we're putting down to advance our machines into this kind of vision for the next sort of 5-ish years. So we're working really hard on advanced memory technologies. You can see our announcements here. We have partnerships with Cerebrus, AMD, and Intel. And these partnerships are looking at things like new materials for memory. So this isn't just take your existing memory and make it a bit better. This is completely redesign how you'd store data in volatile memories. It turns out that you can kind of re-architect how you fab those things, and you can get much higher performance or higher density. And that higher density actually gets you to better performance. And then if you think really hard about how you might stack that, or you might do chip bonding, 3D integration, you can get another large performance improvement. And so we have projects with these three companies that we've just announced to work on this, on these technologies. In the middle here, some of you have probably heard of Cornelis. They're an alternative network choice if you don't buy HPE. Everybody's buying HP in this room, so I'll just say that Cornelis is really good. We're the only places deploying them right now, but we're deploying them in our commodity line, and they're sort of performance cost optimized technology. We're working with them on a future generation of networks, which will bring many of the things we talked about, like photonics, etc., into the picture. And then over here on the right, I wish I had a picture for the vendor and the hardware that we had selected for Vanguard 2. We're working really hard. Rob Hoekstra is the manager for the department, the research group down there, and they're working on that. But you should think about this as novel accelerators beyond GPUs with reconfigurability that we can look at. And there's an advanced storage option in there. So if I was to go back and look at this machine again, and I would say, how would you interconnect those things? You'd probably invest in a really good network company and have network choices that were not vendor defined. They were vendor agnostic. You'd spend a lot of time worrying about memory, and then you'd probably spend a lot of time worrying about data storage and a data infrastructure. And so it's no surprise that these things are here in our R&D strategy on the bottom. Alongside that, although to a smaller extent, we're still working on an R&D in our own labs, in our national labs, to advance machine learning, neuromorphic, which is more of an energy-optimized play, and quantum. We don't have any vendor announcements there, but still working with those architectures. Okay, so I was going to do, this is Sai dreaming on the flight to Riken about what would he talk about, predictions for the near future. So I think for NNSA, it is extremely likely that we will keep going with CPUs and GPUs. We just spent an enormous amount of money porting our codes to these architectures. They run really pretty well, and so it would seem sensible to keep on that path for a while. Anything else is really incredibly costly for what we would call a very bespoke design, which is kind of chiplet optimized for a particular workload. Our system partitions are an appealing way to balance the fact that we don't have a single workload, but we have many fewer than, say, Fugaku with 3,000 users. You might think we have 300 users with absolutely enormous applications, but those applications are very diverse. And so we will probably want to head down this system partition road. Our colleagues at NERSC in particular have demonstrated this in an open science setting, and it seems quite appealing. I personally think there is a path to 5 to 10 exaflops, largely on the path we're on. I think that is mostly realistic if you talk to vendors today, but I am just incredibly sick of talking about HPL. I think it's a totally meaningless metric, apart from one thing, and that's the job that Thuc and I have, is to go and sell this machine to people who pay the bill, who sign the check. And the only thing they want to hear is a single metric, which we're really good at. And until this community has a better metric to offer, which isn't a complicated metric, we're going to be stuck trying to talk about HPL in Washington with the president, saying, is it really the biggest machine in the world? Yes, it really is, sir. And we've got the metric and the runtime to prove it. So this is a very challenging problem, which is nothing to do with technology, but it's something that we need you to help us with. Let me see here. So memory technologies hold really the key to our workload improvements. I think that was clear. We are very kind of interested, but don't have great results yet, talking about concepts like CXL, where we can disaggregate components and then connect them together, maybe in a software setting to try and optimize it for a particular workload. I call these pods of compute. I know that's probably a vendor-loaded term, but it is very appealing for particular things that we're trying to do. And this technology, to me, is really quite interesting for the path that we might pursue. AI and ML, I've had lots of people tell me they will replace our scientists, and we shouldn't worry about all our scientists. We should send them all home and just replace them with ChatGPT. And that's not really the route we're thinking about. We're thinking more that it's an assistant to the users, but not as a replacement. I will say that means that we have to still do an awful lot of HPC and science, and that bit seems to get lost sometimes in the discussion because all we want to talk about is AI, when really we've still got a lot of work to do on the science side of the house. And for us, we're going to be spending an awful lot of time investing in this data infrastructure which we build, which will connect all our labs together and have a very high performance data environment. I will say Lustre as a file system needs to go away, it needs to die, and we need to think about object stores and much higher performance data infrastructure, places to store the data that we're generating. We're still working on that. That turns out to be incredibly hard. So let's talk about the software environment. This, as Thuc said, this is an area that there's just an enormous amount of conversation in DOE. So traditionally what we've done is built every machine, and we've had this army of software people who've optimized the environment for that machine and worked with users to do that. It turns out that's just immensely expensive to do. It's also very frustrating and expensive for our users who get onto every platform and everything is different on each machine. The other observation is there's usually considerable overlap with that between sites, say between Riken and DOE, but even within DOE. So we're working across at least our program, trying to figure out what these common components actually really are and how they're really used so that we can try to produce fewer sets of recipes that really work for our users. And then concentrate our investments in particular kind of combinations of these components, so it makes sense. So the way I would describe that as well is we're trying to make these environments higher productivity. So when you get onto a machine, it feels more familiar. It's not very bespoke and very optimized in sort of peculiar ways, and that you're able to get your application running really quickly. So that'll include things to do with machine learning and our general science workloads, but it will make our users higher productivity when they get there. They'll be able to use it quicker. They'll be able to get the results done. They'll be able to get off the machine and do some great science. And so with that note, Hal Finkel's down there. He's my partner in crime on this. So we talk a lot about this software sustainability activity. People in DOE, well, this will be a hot word for them at the moment. With ECP ending, we try to figure out how to bring the products that we spent a lot of time building for our exascale programs. We've made those really high performance, and we've scaled them out to the largest machines in the world. And now we've got to figure out what the next step with those is. Many of those are international collaborations. They're products that are used everywhere. And so we have to figure out our support mechanism to do that. So you can't really see it here if you're in the audience, but on this right-hand side is sort of an inventory and assessment activity which is underway right now at DOE, where we're going through our applications looking at all the software products that we use, the 71 products that Thuc talked about in ECP, but turns out there's like another 100 of them. And we're trying to figure out which ones of these things are really critical to what we do, things that we've got to invest in to keep them alive, things that the industry or the community would invest in, and then we will develop a sort of funding strategy built around that. That's certainly stuff we're trying to do within NNSA, and I think Office of Science is trying to do an equivalent activity as well. And we'll revise these over time to make sure that those risk matrices are moving towards the high-risk software components that we've really got to have available. So these little risk things down here are kind of the product we're working on right now, and then we'll sort of build a strategy once we have those completed. We should have those real soon. Okay, and then the last thing. So what I will say is this is an area where we think DOE should be collaborating with everyone else in the room, the international sites, because it's highly likely that our software environment is kind of similar to most of the other parts of the community as well. There's one area where that's really, really obvious in its overlap is in planning for Fortran. We have this conversation in DOE about Fortran's dead, it's time to move on. I was glad to see it was in Satoshi's myth paper that it's not dead and that we're keeping it around. 50% of the cycles on our largest machines still run Fortran, right? So it's just really important that we have an answer for this. Now, I think you can go and get a vendor to produce a Fortran compiler for you, and it's really expensive for that vendor to do it, especially if they're a small AI startup or an accelerator company. It's usually very low on their list of things they want to do because the rest of the market doesn't really use it, but it's very important for us. And so we're trying to figure out basically how to have an LLVM answer to that in Flang that's really robust and that really works, so they don't have to build that infrastructure themselves and they can use it. We're some ways through that process right now, but it's not complete. And one of the reasons it's not complete is it's very hard to get feedback from people on the features that it's missing. So that's an area that I think the community as a whole could help us with. And why should you do that? Because if you get that right, you'll have other options for accelerators and other systems that you can buy, because you'll have Fortran support on that hardware, because they'll have a much easier compiler framework to use to get the software to work. So it's important for us, I think, to work with all of you to get this right. It's important for DOE, but I think it's important for everybody. Okay, do you want to do the final thoughts? Okay, this isn't my slide, but there's these 3 reports that we've been working on here. So ASC program is we just have our 25-year report up there. It's been a program which is sort of, I would argue, has built these enormous machines, been very successful in HPC. We've cataloged a lot of that in that report, and I really encourage you to go see it because I think it's a story for lots of people in the room who've worked with us. Just incredibly proud of all the work that's been done. But what's next is in these other two reports. So our simulation strategy lays out a thought about how we will do code development and science moving forward. And our computing strategy is in the how do we work with agencies, academia, international collaborations to ensure that we still have a really viable computing platform to do the science that we need to get done. And so all these reports are sort of in soft release form right now. We can provide those as well. Okay, that's it from Thuc and I. Thank you.
Thank you very much.